Swayam Prabha. Digital India. Educated India.
Welcome back to the course on mechanics and control of robotic manipulator. If you recall the last lecture, we stopped this particular slide. So, where we can say that how to get the relationship between the frame G and B. This is what our main interest. So, why we are actually taking this in order to get the position vector of P with respect to either G or B if one of the relationship is known to us. So, in that sense what I said in the last lecture itself, we will be talking about description of position and orientation in the upcoming lecture. So, let us actually move that. Okay. So, for that one simple aspect we are bringing the assumption that the manipulator or the robot has sufficient number of joints in such a way that the hand or arm could be orient arbitrarily while keeping the fingertip or tool at the same position in space. In the sense, when I actually derive the equation or when I derive the relationship, we assume that these all actually exist. In the sense, so the robot constraint we have not incorporated in this particular description. That is what the whole idea. If that is the case, what we can see, the position vector description we can do. For example, now there is a point Q in a, you can say, 3-dimensional space is given. Can I actually relate this with respect to one of the frame, which is very easy, because we are actually using the Cartesian coordinate system, we simply call CCS. So, in the sense Cartesian coordinate system, which means actually it would be having so x, y and z. So, we usually denote in the, you can say, unit vector, which is I wrote it as a cap. So, what that means? So, this is one of the frame called A. So, the A frame actually would be having zx cap, zy cap and you can say a x cap, a y cap and a z cap all would be there. So, further what we can see, since it is a Cartesian, so this position can be directly written as a position vector. So, what we can write, this is actually a position vector of q with respect to a as straightforward as actually 3 quantity, which I can write qx, so qy and qz. This is very straightforward, right. So, the position vector description with respect to Cartesian coordinate system is not big deal, right. So, we can see that is what I have actually shown. So, there is a frame A and A to Q I have actually seen there is a position vector. So, now you can actually look at it. So, capital P denote with the bolded, this denoted as a vector which is a position vector. So, whatever the you can say suffix which is actually relate to the body or the system. Now, position vector of Q, so whatever I have written on the top, that is with respect to. So, now this I am supposed to write as, so position vector of Q, so with respect to frame A. Okay. So, now you are clear, right, what we would be using as a denotation or what would be our representation. This is what we have written. I hope this is actually not you can say complicated. You can get the position vector of Q with respect to A as 3, you can say scalar quantity which denote as 3 cross 1 as a vector, which is very easy. Let us go to the next one, which is what you call little complex, what you call description of orientation. When there would be a description of orientation will come, if the position is a simple point or the body which you consider as a point, it won't come. Now, there is a 2 body. So, one body which is actually I consider as a ground, there is another body which is actually rotating. So, what I can see, this body would be having xb as the frame and the ground which would be having xa as the frame. So, now I can see that this is orient with respect to this axis, so on so angle I can say, this is what I can say, right. But now this is in the 3-dimensional space. So, how many angle it would be there? So, 3 orientation will come. Can I write it straight away? So, for understanding that, what we are doing, we are actually taking the frame A first, then I have another body which is oriented with respect to A in this form. Okay. So, the body which is having B as the frame, the B frame is actually like orient XB, YB and ZB. Okay. Now, this is the case. So, before going to talk, so I already mentioned that we are going to use only right hand rule in the sense, so the thumb finger would be related to what you call x axis, then the forefinger is actually like denote to y axis and the middle finger is denoted to z axis, right. And you can actually like take for the orientation or the rotation positive direction. So, you can say that the thumb direction you keep your thumb, you can put it in the positive direction of that particular axis, and how the remaining fingers will come, the four fingers, right. So, that is the positive direction of rotation. So, in that sense, if I say that this is the screen where this is x axis and y axis, and I know that the z axis will come outside the screen. So, now what would be the positive rotation? I keep the thumb finger in this way. So, how it is coming? So, it is coming like this, right. In the sense anti-clockwise direction is your positive direction. Okay. So, now why there is a positive direction in counterclockwise if I draw in the screen? So, this is the way. Okay. If I use this z axis this way, then I will say that that is actually like opposite. Okay. Now, I hope what denotions we are actually like using or what representation we are using, that I hope you are clear. So, let us actually like move further. So, what that? So, we can see like if these are there, can I actually like find some kind of idea to give the orientation of B with respect to A. So, obviously, one can see that the A to B there is actually like no straightforward positional information which we did in the earlier. So, then what one can see? So, one can see, can I do some other way? So, what other way? For understanding that, I take one another example. Okay. So, there is a body which is having, you can see XB and XA as projected, in the sense it is actually like collinear. So, only actually like you can see you call the orientation with respect to, you can say XB frame, it is actually like oriented as phi angle. Okay. So, now one easily you can actually like get. So, what one easily get? So, these all unit vectors, if I have unit vector value, can I actually like project it on the frame A? In the sense, can I actually like project the XB unit vector project on the A frame? What I will get? So, in this case it will give a straightforward 1 0 0, right. If I actually like project YB unit vector to A frame, so what that would be? YB will not be projected on X, so that would be giving 0, but what would be projected on YA? So, this is actually like unit vector 1, this would be phi, so that would be giving cos phi. So, what would be the projection on the ZK? So, that would be sin phi, right. The similar sense you can actually like project your ZB unit vector project on the A frame. Okay. What would be the projection? Obviously, that will not give a projection on X, so that would be 0, but this unit vector I project on YA frame. So, what would be? That would be equivalent to, so this is actually like phi, this is 90 minus phi, this is cos 90 minus phi is actually like sine, and it is opposite direction. So, this is minus sin phi, and this is actually like straight away cos phi, right. So, now what we get? So, we will get actually like 3 projection vector which is actually like simple cosines, right. So, in that sense what direction cosines, that too. So, now can I actually like merge these 3 unit vectors? Yes, I can do. So, what that? So, this is actually like XB unit vector projected on A, so that will give 1 0 0. Okay. So, then YB, so YB unit vector projected on A, that would be giving 0 cos phi sin phi, right. So, the third thing is actually like you can see, so the ZB unit vector projected on A frame, that would be giving 0 minus sin phi and cos phi. So, you can see like what it is giving. So, it is giving again another set of unit vectors, but what it is giving? It is giving some kind of information of each unit vector of B projected on A. So now this is what we are actually like going to consider as a combination of these 3 unit vector, which is going to get 3 cross 3. This is what we are going to call as a orientational information, which is simply called rotation matrix. So then now the rotation matrix of B with respect to A can be written this way, like this. So now this is one specific case, right? How can I actually like make it a generalize? So for generalizing, what we can do, we can actually like make it something like the cosine, direction cosine, or you can say projection. So how I can do, I can actually like always say that xb projected on A, okay, this is one unit vector, then yb projected on A, another unit vector, then zb cap projected on A. So now these all make it. So how I can take the projection? It is straightforward. So you can actually like take simple dot product, that is what will be obtained. You can see in that. So this is what we are actually like rotating in the sense. So yb frame, or you can say yb unit vector projected on A. So xb unit vector projected on A, zb vector projected on A, that is what the meaning. So now we will actually like see this is what we have written, but this how I can write? I can write as a dot product of 2 unit vector is the cosine, right? So now what dot product I can take? So I can take the dot product xb cap to xa cap, xb cap dot product with ya cap, and xb cap dot product with za cap. So now you can actually like recall what we did in the last case. So we said that this is yb, okay, and this is actually like zb cap, right, and this is what you call phi, and this is phi equal, right. So now this is actually like you call ya, and this is actually like za, right. So you can recall what we did. So now this is 1 and this is 1, so the direction cosine what would be here? So yb cap dot ya cap, so what would be? This is 1 dot 1, then what happened? So this is 1 1, and this is actually like direction cosine cos phi. In this case, so yb cap dot into za cap should be 1 and 1. This is actually like what angle? So the angle is actually like 90 plus phi. So you can say cos 90 plus phi is actually sin phi, so that would give sin phi, right. So this is what we also obtained, right. So that is what it is in this case. So in this case it is 0 angle, so this is 1 dot with 1 1, this is actually like 0 and 0. So now that we can write as a generalized, you can see this is the way we can write a generalized rotation matrix. You can see this is xb projected on A frame, yb projected on A frame, zb projected on A frame, right, you got it. So now each you can say column would be a unit vector. So obviously you can see like this is also like giving a set of unit vectors. So now you can see even these unit vectors how the nature, so the nature is actually like one perpendicular to another in the sense. So these 2 unit vectors are orthonormal, these unit vectors are orthonormal, these 2 unit vector if you take orthonormal, in the sense what you can see this rotation matrix is consist of several orthonormal vectors. So obviously if you take the determinant of R, so what that would be? So the determinant would be 1, okay. So now this kind of case is what we call a orthogonal matrix. So that is what we are saying, since it consists of orthonormal vectors, so it can be called as orthogonal matrix. Therefore, so what you can see, so you know RBA inverse, you can write, so adjoint of RBA which is equivalent to transpose with determinant of A, right. So what this is actually like RBA transpose, and this is equivalent to 1. So in that sense what we denote, if you want to know the information of A with respect to B, this is supposed to be equivalent to, so this whole inverse, but this inverse is equivalent to simple transpose of this. So now we got some kind of very easiest you can say form. So now this form how we can use, this can be used as an operator, this can be used as a mapping tool, this can be used as some kind of you can say information related aspect, right. So that is what we are actually trying to see in the next slide. So what we are trying to see, this is what we have found. So based on this condition, what one can see, this rotation matrix can be used as, you can say, several form. So what are the forms? One is actually like you can use for mapping, in the sense it can represent the coordinate transformation, in the sense it can map and relate the coordinate of a given point to two different frames if there is a orientation exists. So what the next one can be used? So it can be used as a description of a frame, simple. This is what we are going to use in further and further. So what it gives the orientation of a transformed coordinate frame with respect to another, you can say, frame, or you can say coordinate frame. This is what we did, that is what we say, description of orientation. What would be the next thing? It can be used as a simple operator. So what that mean? It can be used for actually like rotating existing vector to a new vector. It can be used as an operator. So now you can see that the mapping can be done, and further what you can see, we have already defined what is description of position and orientation. So now the rotation matrix can be found, which is actually like one of the orthogonal matrix classes. So I am not talking about Euclidean class and all, it is one of the special Euclidean class matrix, but we are not talking about that in here. But what one can see, we found one of the thing as a position vector, the other thing what we call as a rotation information, what you call as a rotation matrix, or you can say orientation information, we got it as a rotation matrix. So let us actually like move further. So we know like mapping means not only this. So what mapping means, which we have started at the very first slide. So mapping means we are actually trying to relate a mathematical relation from one body to another body, or one set to another set, right? So if that is the case, what are the forms which can come in the motion idea? So it can be two translated frames, or two orientated frames, or two general frame, in the sense it consists of both translation and rotation. So that is what we are actually like trying to see. We can map involved two translated frame, which is we call pure translation. So mapping involved rotated frame, which is we call pure rotation. And finally what we are interested here is the general body motion, which can have both translation and as well as rotation. This is what we are actually like interested. So if that is the case, so what one can see from the generalized pictorial view from the, you can say, the mathematical relation. So what we can see, we can start with the frame A. Okay. So the frame A would be consist of three you can say mutually perpendicular unit vectors. So now the body, which is we call B. So the B is consist of what? Another body frame, which is you can say the frame B. So now I have one simple idea. If I have a positional information of Q with respect to B, if I have, further I can actually like derive this. Can I get this? Yes, I can do. So that is what we are actually like trying to do. So you can see that if this information is available, further the translational information of these two are available, we can find this. In the sense, position vector of Q with respect to A we can find, provided what? The positional information of B with respect to A is known. Okay. So that is what we are actually like trying to show here. So in the sense, what would be, by looking the diagram itself, you can see the Q can be written as this, but this can be simply written as the vector addition of this, in the sense. So PQ with respect to A can be written as, so P BA plus PBQ, in the sense position vector of Q with respect to B and position vector of B with respect to A. Some people even see that this is matching, then this is the transformation is done. So now this is what mapping between, or mapping involved translated frame. It is straightforward, right? It is simple, what you call vector addition. So let us actually like go next one, which is mapping involved rotated frames. Is it anything challenges? We can see, so obviously there are two frames we are taking, so body 1 and body 2. So the body 1 we assume that initial frame, which is A, and the body 2 which is we call B frame. So now again there is a point Q, which is actually like one of the information is known with the sense. So PQ with respect to B is known. So how I can actually like find PQ with respect to A? So I need one additional information, right? So what information? How the frame B oriented with respect to A I should know, in the sense the rotation matrix of B with respect to A, if I know, I can actually like bring this, right? With the help of this, I can actually like find this. What one can actually like easily see, this is the rotational information. If I rotate opposite direction of this, so what I will get? I'll get this Q with respect to A. In the sense what one can see easily, so we can see the position vector of Q with respect to A, simply rotation matrix of B with respect to A multiply with the position vector of Q with respect to B, right? So this is another information which we obtain, right? So what that, this is mapping involving rotated frames, you can find that. So this is what we have actually like obtained. So now we will come to the general case. This is the last slide of us. So we can see that how it can be done in this lecture. So we can see like this is A and the point we have frame, okay, the coordinate system, and B also have a coordinate system, which is you can see by looking itself these two are oriented. So now what information I should know? The rotational information of B with respect to A and the translation information of B with respect to A should be known. So now these two informations are known. Can I actually like find on any arbitrary point Q with respect to B I know? Can I actually like find the position information of Q with respect to A? Yes. First what supposed to do? So first you have to actually like orient this in such a way that that would be make it parallel, then we can do the vector addition, right? So then what we can actually like expect? So we rotate the, you can say the Q vector, okay. So the Q vector, so we will actually like make it first parallel to A, then we do the vector addition. So now this is what the you can say mapping involving translated and rotated frame. So now you can see like if this B is associated with A, in the sense these two are same point, this is what we do. Similarly, if we assume that there is no rotation, so what we will do, this assume that identity matrix, this is what we do, right? But in this case it is not. So first we rotate and then translate. You got idea, right? So this is what we have actually like seen as mapping involved a translated and rotated frame. So now what we obtained one straightforward relation, okay. So this relation we are going to use further and we will bring some kind of relation further and further. So what this dimension is 3 cross 1 and this dimension is 3 cross 1 and this matrix dimension is 3 cross 3 and this dimension is 3 cross 1. So in the sense overall the dimension is 3 cross 1, okay. So now the next lecture we will see how we can get into a single entity, okay. So that is what we are actually like identifying in the next lecture. So now with that I am closing this particular lecture. See you then, bye, take care.